Welcome to Lecture 1.1, Basic Set Theory. Let us begin with the question of what is a set? Now, almost everybody, regardless of mathematical background, has an intuitive idea of what a set is. It's a collection of objects, sometimes called elements. Sets, of course, can be finite, or they can be infinite. We can talk about the set of all people, which is a finite set, or the set of all numbers, which is going to be infinite. For some examples, let's let S be the set consisting of 0 and 1. We'll write this using this notation. S equals, these two curly braces, means that the things that we put inside are the elements of the set, 0 and 1. Let S be the set of words in the dictionary. Of course, you have to make it clear which dictionary we're talking about, but that is definitely going to be a finite set. We can talk about the empty set, which is the set that contains nothing. It has 0 elements in it, and we'll often write it like this, with a 0 with a line through it. Here's a set. Let S be the following 4-element set: the number 2, the capital letter A, the word cat, and the set 0, 1, which we saw up here. That is a set. Now, repeated elements in sets are not allowed. So in other words, if we try to write down the set containing 1, 2, 3, and 3, we can do that, but it's the same as the set containing just 1, 2, and 3. Now you may wonder why we would ever write something like this down when we could just write that, but there actually are a lot of cases when we want to do something like this. For example, what if I said let S be, it's not a very good S, but well, let S be the set of all elements of the form -1 to the n, where n is an integer. So like 0, 1, 2, 3, etc. Now it's not hard to see that -1 to the n is either 1 or -1. So we could write this as -1 to the -2, -1 to the -1, -1 to the 0, -1 to the 1, -1 to the 2, -1 to the 3, -1 to the 4, and so forth. But just because we write it like this does not mean it's an infinite set, because -1 to an even power is 1, like this, and the -1 to an odd power is -1. So really, this set right here just contains 2 elements, +1 and -1. So this might be a little toy example where we write 3 twice, but there's a lot of times when we write a set containing possibly, seemingly an infinite number of things, but it collapses down to maybe even a finite set like this. That said, there are scenarios when we want to allow repeats explicitly, and we can do this by using an object called a multiset, where repeats are built into the definition. For example, I can talk about going to the vending machine and getting a drink for me and 2 friends for lunch, and maybe the 3 drinks that I get are a Coke, a Sprite, and another Coke. And I don't want to write this, I don't want to say that's the same thing as the set containing a Coke and a Sprite, because I actually got 3 drinks instead of 2. So I can write this as multi-sets. However, these things technically as sets would be equal. So there are some times that we want to use multi-sets, but for most of the things in this class we will be using sets, and if we don't specify otherwise, we're just going to assume that if we use these curly brackets that we mean set and not multi-set. And sometimes some books and some papers use an alternative notation for multisets. Like I've seen double braces like this, or sometimes double brackets like this. Now, one thing that I am not going to do is give a rigorous mathematical definition for what a set is. I think that it suffices to talk about informally a set being a collection of objects which are called elements. And the reason is that it's actually difficult to formally do this. The problem is that some sets actually cannot exist. Well, some things that we think could be sets could not exist. For example, if we try to define the set of all sets, we will run into a problem called a paradox. The following is called Russell's paradox due to the British philosopher, logician, and mathematician Bertrand Russell. His picture is shown here on the right. Suppose a town's barber shaves every man who doesn't shave himself. Then, who shaves the barber? Now, at this point, I encourage you to pause the video and convince yourself why this is a paradox on your own time. It shouldn't take too long. Basically, if the barber shaves himself, then by definition, he can't shave himself. But if he doesn't shave himself, then he has to shave himself, because he shaves every man who doesn't shave himself. So again, I encourage you to pause that if you didn't quite get it. Now, consider a set-theoretic version of this. Consider the set S of all sets which do not contain themselves. So suppose such a set existed. Now we ask, does S contain itself? And this is basically the same type of paradox as Russell's, just phrased in terms of sets. So if S does contain itself, well then that's a problem, because by definition S contains only the sets that do not contain themselves. But if S does not contain itself, then that's a problem, because then by definition it has to be in S, so it does contain itself. So this is a paradox. So how do you resolve it? You could say, well, perhaps a set can't contain itself, because let's try to write down a set that contains itself. It's actually really hard. So let's take a set, maybe 1 and 2, and okay, now if it contains itself, it has to contain the set containing 1 and 2, and well, now there's a problem. So can you make a definition like this? It'd have to be some sort of recursiveness. And this is a bracket, not a 3. Sorry about that. Well, so in terms of the elements, it's hard to write down such a set, but let me actually write down one a little less explicitly. So let S be the set of all things, people, places, numbers, ideas, etc., all things that are not trees. Well, so the set of all people is in here. All people, all places, all numbers, all equations, all ideas, everything except a tree. Well, this set is not a tree, so it has to be in here as well. So this is a set which, if it exists, contains itself. So it's not clear at all whether or not this set actually exists, because maybe if it does exist, you could come up with a similar paradox. So the moral is it's hard to write down a set that contains itself in terms of the elements, but you can ideas write down such a set, but it may or may not exist. And that's why it's so hard to define what a set is mathematically, formally. So we just say it's a collection of elements. And if you want to know more, take an advanced course on set theory. Later in this class, we will encounter paradoxes that are not related to sets, but are logical statements. For example, such as this statement is false. And this is a very similar type of paradox as these two above. Is this statement false? Well, if it's false, then it's true. But if it's true, then it's false. Okay, so that's the tip of the iceberg. And what I really want you to take from this slide is that the set of all sets do not exist, and a lot of other sets that you might think you could write down don't exist. So you have to be really careful with how you define a set. Okay, so let's talk about some notation and some examples. So we will usually denote a set by a capital letter like A or B or S. Now, if X is an element of A, we will use this notation. We will write this symbol, which means is in, so X is in A, or is an element of A. Otherwise, we will write the in symbol with a line through it, like this. So X is not in A. Now this in symbol looks a lot like an epsilon in the Greek alphabet, but it's a little bit different. Let's now introduce some notation for some commonly used sets. The first one are the natural numbers, which we denote by capital N, and these are the whole numbers. Now, some books and some resources will include 0 as a natural number, and others don't. So it's not consistent throughout the literature. We are going to include 0 as a natural number, but just be aware that not all sources do that. Some of them just say the natural numbers are beginning at 1. Next are the integers, which are all whole numbers, positive, negative, and 0. And we usually use the letter Z to denote these due to the word Zahlen in German, which means number. Next are the rational numbers, which we usually denote by Q for quotient. And these are the set of all fractions of the form A over B, where A and B are integers and B is non-zero. So this type of way to write a set, sometimes called set builder notation, it's just an alternative if you don't want to or can't really list out all of the elements like you do with the integers or the natural numbers. Next is the set of real numbers, which we denote by R. And I'm not going to use any notation to denote the set because I think it's pretty clear what we mean by this. And finally, the complex numbers denoted by C. You probably know what these are anyways, but just to be clear, they are the set of all numbers of the form A plus BI, where A and B are real numbers, and I squared equals -1. Or some people might like to write that I equals the square root of -1. Either of those are fine. Sometimes we will want to speak of sets such as the non-negative rational numbers or the non-positive real numbers, and we can use little subscripts of greater than or equal to 0 or less than or equal to 0 or things like that to denote those sets. I think it's usually clear from the context of what we mean. Now we could write things like this. We could say this is a set of all elements Q such that Q is at least 0. There's a lot of ways we could write this. We could instead say this is a set of all fractions A over B, where A and B are natural numbers, and B is not equal to 0. So there's not one unique way to write a set using this so-called set builder notation. Now hopefully you've gotten this from context, but just to clarify, a vertical line in these notations means such that or where, and we can also use a colon for this. Commas are read as and by that I mean this type of comma. So we say A and B are integers and B is non-zero. And finally, as I said above, there are often multiple ways to describe a set. So here's a simple example. Consider the set of all real numbers such that x squared minus 5x plus 6 equals 0. Of course, you could just write this as a set of all x such that x is real and x squared minus 5x equals -6. And if you think about it, the simplest way to write that is just the set containing the numbers 2 and 3. continuing with notation, we say that a set is finite if it has a finite number of elements. Otherwise, it is an infinite set. The number of elements in a set is called its cardinality, although often I'll just say size because it's a shorter word and it's easier to say. And we usually denote it with vertical bars, like you would the absolute value of a number. If A is infinite, we may write that the cardinality of A is equal to infinity. At this point, I should probably mention something that we are going to see later, which is that there are different infinite cardinalities. In other words, there are different sizes of infinity. This is the concept that the first time you see it, it seems shocking, like it can't be true. But I'm mentioning this because when we write that A is an infinite set here, we're not saying how big A is. All we're saying is that it is not finite. Now we come to the concept of a subset. Suppose we have sets A and B. We say that A is a subset of B if and only if every element of A is an element of B. Let me draw a quick picture of this. So suppose that A is this set. Maybe this is finite, maybe this is infinite. This is sort of a cartoon way to draw the set A. Then A is a subset of B if B is basically if B is a bigger set, if it contains everything in A and possibly more. So we write this using a symbol that's sort of like a less than or equal to sign, but it's curved. So we say A is contained in B, or A is a subset of B, or we can flip it around and write B is a superset of A, or B contains A. At this point, I need to give you a couple of warnings. First of all, with notation or numbers, if I write x is less than or equal to y, that is distinctly different than writing x is less than y. They mean different things. This first one allows for the possibility that x and y could be the same, where the second one is saying x is definitely smaller than y. Unfortunately, this subset notation is not analogous. And by that I mean if you remove this line underneath the subset symbol, unfortunately it means the same thing. Because of that, I think it is ambiguous if you remove this. So this symbol here, it really should be the case that this means a subset, but not equal. But unfortunately, there's plenty of books out there that don't use it that way. So even if I make that convention, you could go out in the world and see a lot of sources that use this to mean subset possibly equal to. So because of that, I will try to exclusively use this symbol for subsets rather than the other one. Now in this class, if we want to say that there are elements in B that are not in A, in other words, if we have a subset but we do not have equality, then we can do that by adding a little diagonal line on this bottom horizontal line. We write it like this. In that case, we say that A is a proper subset of B, or that B is strictly larger than A. Both of those mean the same thing. Now, this is something we could do with numbers. We could say that x is less than or equal to y, and if we put a line there, you probably know what I mean by that, but of course we have a symbol reserved for that, just the less than symbol. But unfortunately, for sets, that symbol does not necessarily imply strict inequality. Finally, the last thing that I want to say about this slide is the term if and only if that I used up here. Now technically, logically speaking, the terms if, the terms only if, and the terms if and only if mean different things. And it all has to do with whether x implies y, in other words, if x then y, or if y implies x, if y then x, or if both of these hold. If x then y, if y then x. We'll be talking more about this in a later lecture, so I don't want to spend too much time on it now, but I just want to tell you that when you see something like if and only if, you should think of this as meaning is equivalent to, or in other words, can be defined as, or is identically. And the reason for the difference is because how we say things colloquially is often a little bit inconsistent with how we say things logically. So speaking mathematically, we don't always speak perfectly, logically, mathematically in our everyday life. And as a simple example of this, imagine that you go to the restaurant and there's only one thing on the menu. You might say, well, I have no choice. I have to get that menu item. However, a mathematician will say, well, you have one choice. And if there's two things on the menu, you could say, oh, I have two choices. A mathematician will say, well, you have one choice. So that's just one of many examples of where our colloquialisms do not necessarily match with what a logician would say. But we're going to save all of that for a later chapter. Finally, I want to conclude this slide with an example of something that you probably think is obvious, but I'm mostly putting it in here so you can get used to the new language and notation that I've introduced. So the natural numbers are contained in the integers, which are contained in the rational numbers, the quotients, which are contained in the real numbers, which are contained in the set of complex numbers. And of course, all of these inequalities, or these subsets, are strict. So I can put these little lines here to denote that. The remainder of this lecture will be about basic set operations like intersections and unions and things like that. These are likely concepts that you already know. Maybe you saw them in high school, but I still need to introduce them formally for completeness. And also, it's good practice to get used to our new notation for sets. So first is the intersection of sets, A and B. This is the set of all elements that are both in A and B. So we use this little symbol to denote it. It's like an upside down U. So we can write this as either, or we can say this as A intersect B, or just the intersection of A and B. Both are valid. And by definition, sometimes this colon equals means by definition, it is the set of all elements X such that X is in A and X is in B. Two sets are disjoint if they have no elements in common. In other words, if A intersect B is the empty set. Now, quick minor comment. I'm saying if here. I really could say if and only if, but I'm not, just because I'm making a definition, so I think it should be clear from the context that that's what I mean. Finally, the union of sets A and B. This is the set of elements that are in either A or B. So we say A union B, or the union of A and B, and we use this symbol that is sort of like a U. And by definition, this is the set of all X such that X is in A or X is in B. Let's do a few examples. So if A is the set containing 2, 5, and 8, and B is the set containing 7, 5, and 22, then A intersect B is just the set containing 5, and the union is the set of all numbers in either of these sets. So that's 2, 5, 8, 7, and 22. Recall that we don't allow repeats. And also something I didn't say before, but maybe I should have, is that the order doesn't matter. We're just concerned with all things that are in the set. So in other words, the set containing 2, 5, and 8 is exactly the same as the set containing 8, 5, and 2. Next, the union of the integers and the rational numbers is the rational numbers, because everything in here is also a rational number. And the intersection of the integers and the rational numbers is the integers. Now this holds more generally if we have a set A, which is a subset of B, then convince yourself from this picture that A union B equals B, and A intersect B is equal to A. Example 3. If we take any set A and union it with the empty set, then we get back A, because we're throwing in nothing. Our next topic is set complements, which, roughly speaking, is the set of everything that is not in the set. But before we can define such a thing, we have to talk about what world we're living in. So often we need to establish the set of all elements U under consideration, which we will call the universe. For example, if I want to talk about the set of elements that are not in the set of integers, well, obviously 1/2 is not an integer, but what about a car? That's not an integer, right? But I don't necessarily want to include cars in the discussion if I'm just looking at numbers. Now that may seem like a ridiculous example, but what about, sometimes it's not clear whether I want to include real numbers, maybe irrational numbers, or complex numbers if I want to speak about something like the set of non-integers. Here's our definition. The complement of a set A is the set of all elements in the universe U that are not in A. So we write this as follows: A with a superscript C, which is the set of all x in U such that x is not in A. For example, suppose A is the set of natural numbers, and we're going to include 0. Let me ask you, what is the complement of A in the following cases of the universe? So if the universe is a set of integers, Z, then in that case, the complement is the set of all numbers, the set of all integers, such that x is less than 0. And here I'm using my colon instead of a vertical bar. Remember, they mean the same thing. So for part 2, if my universe is a set of rational numbers, then A complement is the set of all A over B, where A and B are integers, B is non-zero, and then A divided by B is not an integer. So I have to write that B does not divide A. So in number theory, this is the divide symbol. So B does not divide A. Or equivalently, A is not a multiple of B. For part C, if our universe is a set of all real numbers, so this is the set of all real numbers x. Sometimes I can write things like the set of all real numbers where x is not a natural number. So this is a different way to write, a slightly different way to write the same thing. And similarly, for part 4, if we use the complex numbers, C, I could do the same thing here, just use C instead of R. And finally, this is an important case. If my universe is the natural numbers, then there is nothing in my universe that is not in my set A. So in that case, the complement of A is the empty set, which, well, I should probably write that. It's easier to write it like that. I want to leave you with a couple last thoughts. First of all, sometimes the complement is denoted with a bar, so like this instead of an exponent C. So I'll mention this because some books and resources you'll see will write it like this. And finally, I have not defined a Venn diagram, but you've likely seen them in different contexts. We'll talk about them very shortly. But in this case, the complement of A is just the set of, it's the shaded region that's outside of A. So it's everything that's in our universe U, but not in A. So this is a nice visual way to represent what the complement is. Often, we want to speak of the complement of a set with respect to another set? Well, formally, if we have sets A and B, then the complement of A relative to B is the set of all elements that are in B but not in A. So one way we can notate this is with a subtraction sign. So we say B, sometimes I'll say B take away A, or the complement of A relative to B, is the set of all elements X such that X is in B and X is not in A. The symmetric difference of A and B is the set of elements that are in one of these sets but not the other. So there are several different notations for this. One of them that I will use is a plus with a circle around it, but you also might see things like a triangle, so something like this, and there's a few other ones as well. These are probably the most common. So this is the set, I'm going to say A take away B union B take away A, because I think that's just more natural than saying the complement of B relative to A. And the way to visualize this, I think, is with a Venn diagram. So the symmetric difference is literally this region union that region. So it's the elements that are in one of these sets, but not both. Finally, it's worth mentioning that sometimes the complement of A relative to B can be denoted with a backslash instead of a minus. And the reason for this is because some people want to use a different symbol than subtraction, because subtraction is for numbers, and this is for sets. Okay, let's do a few examples. So let's compute the complement of B relative to A, or A take away B, the complement of A relative to B, and the symmetric difference of A and B in the following three cases. So first of all, A is the set 1, 3, and 8, and B is the set 2, 4, and 8. So to visualize this, let's call this A and let's call this B. Then A contains 1, 3, and 8, and B contains 2, 4, and 8. So the complement of B relative to A is 1 and 3. So that's so A take away B is 1 and 3. And then the complement of the complement of A relative to B, see, I find it much easier just to say B take away A for this reason, is 2 and 4. So let's write that down. So B take away is 2 and 4. And then the symmetric difference are the things that are in both of these things. So this is 1, 3, 2, 4. Recall that order within a set does not matter. Okay, next, any set A and the empty set B. So if we have A and we take away B, so we are taking away nothing, then in this case, let's stick with my colors. A take away B is equal to A. Similarly, B take away A, well, there's nothing in, so B is empty. So that has to be B, which is the empty set. And then the symmetric difference of A and B has to be A. And then finally, when A is equal to R and B is equal to Q, so these are the real numbers and these are the rational numbers. Now, this is a special case of a more general thing where A is a set that contains a set B. So in this case, if we do A and we take away B, so that's going to be the set of all things that are in A but not B. In this case, these are the irrational numbers. Sometimes we'll write this as explicitly R take away, I'm going to use the other notation now, R take away Q. And then what are the things that are in B without A? Well, there's nothing in B that's not an A, so that is going to be the empty set. Now, as I've already showed you, and I'm sure you've seen elsewhere, a useful way to visualize a small number of sets and their intersections, unions, and relative complements is with the Venn diagram. You likely know this from well before this class, even if you've never taken a math course before, from social media, which has caused these to become mainstream, often in the form of memes, though they are often used technically incorrectly. So here's one of my favorites. It's technically incorrect, but I think you should get the idea as to what it means. So this green circle is supposed to be the set of people, or the set of creatures that have been resurrected from the dead, not just an adjective. And then this red circle is the set of creatures whom locals fear and revere. And this pink circle is the set of people, or the set of creatures that converts followers. And then if you look through all of the literature and fiction and movies and so forth, you can probably find more than just zombies that are both resurrected from the dead and convert followers. And there's probably more than just Frankenstein that are resurrected from the dead and whom locals fear and revere. And there's probably more than just Dracula that falls into these two categories as well. So these are not the complete intersection of the sets, but they're put here to be funny. And then, of course, Jesus Christ has the, I don't know, maybe unique distinction that he was resurrected from the dead, locals fear and revere him, and he converts followers. Or so a lot of people believe. Certainly not universal. Next up is the Cartesian product of sets A and B, which is a set of ordered pairs. So we denote it with this little X symbol, A cross B, which is the set of all ordered pairs A and B, such that little a is in the set big A and little b is in the set big B. For a few examples, let's let A be the set 1, 2, 3 and B be the set 4 and 5. Well then, the set A cross B is the set 1, 4, 1, 5, 2, 4, 2, 5, 3, 4, and 3, 5. And of course, order doesn't matter. The order of these pairs doesn't matter, but the order within each pair does matter. So 1, 4 is in here, but 4, 1 is not. However, B cross A, this next one, we're taking, we're basically reversing these. 4, 1, 5, 1, 4, 2, 5, 2, 4, 3, and 5, 3. And of course, we can also do B cross B or A cross A. So A cross A is going to have 9 elements, 1, 1, 1, 2, 1, 3, and so forth. You get the idea. 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, and 3, 3. Similarly, we can define the Cartesian product of 3 or more sets relatively easily. So A cross B cross C is a set of ordered triples, A, B, C, where A is in the set big A, B is in big B, and C is in big C. It is common to use exponents if the sets are the same. So if I write something like A squared, I mean by that A cross A, and A cubed is A cross A cross A, and so forth. And we can also define the infinite Cartesian product as well, but there are some technicalities, like how I've mentioned there are different sizes of infinity, and sometimes this does matter, though often it's understood what size we're using, but I'll come back to that later when we deal with these infinite cardinalities. Next are power sets. The power set of A, you gotta love that name, is the set of all subsets of A, and we sometimes denote that as P of A with the script P, and make sure that you include both the empty set and the full set A. Let's do some examples. So the power set of the empty set contains just one element. It's the set of the empty set. We have to be careful now. It's not just the empty set. It's the set containing the empty set. Those things are different. Next, the power set containing a one-element set, let's just say the set containing 1, consists of the empty set and that set itself. There are no other subsets. Next, the power set of a two-element set, let's just say that that set contains 1 and 2, consists of the empty set, the set containing 1, the set containing 2, and the entire set, that is, the set containing 1, 2, and 3. Let me ask you, do you see a pattern for how big the power set will be if A is an n-element set? And let me just give you a hint here if you don't see it already. So the size of A and the size of the power set of A. So here A has size 0, or cardinality 0. The power set has size 1. The next one, A has size 1. Sorry, A has size, A has size 1. Looking at the wrong one. And the power set has size 2. Here, A has size 2. And the power set has size 4. So notice this is 2 to the 0. This is 2 to the first. And this is 2 squared. So we'll talk later about how to prove something like this when there's a very obvious pattern. You don't want to prove it for infinite many values of n. That would, that's unnecessary, especially when the pattern seems to be so obvious. So we'll talk more about proof techniques later in the class. But for now, let's just, let me take a set A. Let's say it's A, B, and C. And we want to talk about, let's put in a D in there as well. Let's talk about how many subsets there are. So one way to think of a subset is to highlight which elements we want to include and which ones we don't. So if we want to include A, C, and D and exclude B, we can denote that with 1, 0, 1, 1. So this corresponds with the set containing A, C, and D. Similarly, 0, 0, 0, 0 corresponds with the empty set. 1, 1, 1, 1 corresponds with the entire set. A, B, C, D. And it's not hard to see. We'll do this more in a lecture coming up, that there are 2 to the, in this case, 2 to the 4. In general, 2 to the n, I'm going to call these bit strings. And that these are, we say, in bijection. They are in one-to-one correspondence with subsets of A. And so the answer to this, of course, is, let's just say the answer of this is 2 to the n. And so because of this, one alternative notation for power sets that you may see is, so instead of P to the A, a lot of books will just write 2 to the A. And so this is not a number. This literally stands for the power set, even if A is an infinite set. This notation still makes sense. And it's motivated by the observation that if A is a finite set, then the power set has size 2 to the n, where n is the order, or I should say the cardinality of A. Okay, so we are nearing the end of the basic set theory lecture. So here's something else that you've likely seen before, probably in calculus, is summation notation. So recall that addition is a binary operation, and that just means that it is an operation that takes 2 inputs. So for example, x plus y. This is as opposed to, say, a unary operation. For example, x squared just takes 1 input, x. So binary because it takes 2 operations. And we say it is associative, which loosely speaking means that parentheses are permitted anywhere but required nowhere. So as such, we may write something like a1 plus a2 plus a3 plus a4 equals a1 plus a2 plus a3 plus a4. And because we don't need parentheses, we can just write that as a1 plus a2 plus a3 plus a4. And because we don't need parentheses, we can use a concise notation. This is called summation notation. We say it's the sum of ak from k equals 1 up to 4. So A1 plus A2 plus A3 plus A4. So this is called summation notation. So a finite series is an expression of finitely many terms. So for example, like A1 up to AN, we can write that as follows: the sum from k equals 1 up to n of AK. Now the variable k is called the index. The expression AK is sometimes called the general term of the series. And the values below and above the summation symbol are the initial index and the terminal index, respectively. Another associative binary operation is multiplication. The product of elements A1 up to AN is written in product notation using a capital pi instead of a capital sigma. For example, the product of n elements, let's say A1, A2, all the way up to AN, we write this with this product symbol from k equals 1 to n of AK. And of course, we can put parentheses anywhere here that we want, though they are required nowhere. So it's worth noting a few things before we finish. First of all, that there are certainly everyday binary operations that are not associative. And the simplest example of this is subtraction. So 5 minus 3 minus 2, we can't just leave it like that, like we can with addition or with multiplication, as that's ambiguous. It depends on where we put the parentheses. So 5 minus 3 minus 2, this is not equal to 5 minus 3 minus 2, because this first expression is 2 minus 2, which is equal to 0, which of course is not equal to 5 minus 1, which is 4. So subtraction and similarly division, these are not associative binary operations. Another comment, you've likely seen the concept of an infinite sum. So everything here we're doing is finite, but you can of course at least write the formal expression for an infinite sum. It may or may not converge. You can certainly write k equals 1 up to infinity, something like this. Whether or not this converges, of course, depends on what the AKs are. So for example, 1/2 to the k for k equals 1 up to infinity is equal to 1. We say that converges, but if we try to say 1 to the k, that diverges. Sometimes we say this does not exist, or this, we could say it equals infinity, which just means that it diverges. So we're not going to really talk about infinite sums very much. This is a discrete math class, and to talk about infinite sums, we need to talk about convergence, which means we need to talk about epsilon and deltas and continuity. But it's worth knowing that you should know that those things exist. And similarly, infinite products, they're a little harder to define. They're easy if one of these guys is equal to 0. Otherwise, we are getting in the realm of continuous math instead of discrete math. On the previous slide, we saw two associative binary operations on numbers, and we've actually already seen several associative binary operations on sets. For example, unions and intersections. So suppose we have n sets, A1 up to AN, then I claim that, well, intersection is associative because A intersect B intersect C is equal to A intersect B intersect C. Both of these are just the elements that are in A, B, and C. And similarly, A union B union C is equal to A union B union C. These are the elements that are in at least one of A, B, or C. So expressions like this, parentheses, are required nowhere, so we can use a notation similar to a summation notation to denote these. So we write the intersection from I equals 1 up to n of AI, or we can use k if you want for an index. And here we write this expression as the union from I equals 1 to n of AI. Now, Cartesian products, I should actually say, are technically not associative. And that's because, well, technically, I feel like I have to mention this, A cross B cross C is technically not equal to A cross B cross C. Well, why? Because, well, elements in B cross C are ordered pairs of the form BC. So technically an element in A cross B cross C is an ordered pair of A and an ordered pair BC, which is technically a different thing than an ordered pair consisting of the pair AB and C. So technically these things are different, but as we've said before, we can, if we don't include, I've defined the Cartesian product of multiple sets without parentheses just as a set of ordered n tuples. So when we write something like this, what we are really talking about is the set of n tuples A1, A2, up to AN, and this we can certainly use a notation like this. Similarly, for symmetric difference, we can find a similar notation. But we have to be careful how we generalize from 2 equals n. So here, I want you to convince yourself, pause the lecture if you need to, that A, the symmetric difference of A and B and C is equal to the symmetric difference of A and B and of C. So in all of these cases, this is the set of all elements such that X is in exactly one of A, B, and C. So I encourage you to pause this lecture and convince yourself of this. It's just a straightforward exercise, nothing tricky. So that's how we're going to define the symmetric difference of n sets here. Okay, so a few quick examples. So here's 3 sets. A1 is 0, 2, 3. A2 is 1, 2, 3, 6. And A3 is negative 1, 0, 3, 9. The intersection of these 3. So what are the set of elements that are in all of these? Well, let me see. So I see 0 is not in here, 2 is not in there, and 3 is not in, no, 3 is in all of them. So it's just the set containing 3. So what's the union of these? So we don't have to list them in order, but let's do it just to make sure we don't miss any. Negative 1, 0, 1, 2, 3. I don't see a 4 or a 5. I see a 6. And I see a 9. I think that's it. That's the union. I'm not going to do the cross product of these things. I mean, maybe I'll get you started. So 0, 1, negative 1. And then there's a whole bunch of them. And we are going to finish with 3. The order doesn't matter. Let's finish with 3, 6, 9. And there are how many elements? Let's just count how many elements. So there's, how many triples are there? There's 3 times 4 times 4. So what is that? 3 times 4 is 12. Times 4 is 48. So 48 elements. So fill in the details if you want, but I think you probably don't need to. And finally, the symmetric difference. What are the elements that are in exactly one of these? Well, 0 is in 2. 2 is in 2 of them. 3 is in all 3 of them. 1 is in only that set. 6 is in only A2. Negative 1, I think, is only in one of these. 0 we've seen before. 3 we've seen before. So the symmetric difference is the set consisting of 1, negative 1, and 9. Oh, and also 6. There we go. Okay. Finally, we come to the distributive laws, which tells us how 2 different binary operations interact together. So, for example, if we multiply A times B plus C. Obviously, we need parentheses in here. And this is equal to A times B plus A times C. Similarly, if we have sets, we write A intersect B union C, or A union B intersect C. Now there are alternative ways to write this, and I think the best way to see this is just with Venn diagrams, A, B, and C. So if this is A, B, and C, so this first expression is everything that is in A and B union C. So B union C is this here, and so everything that is in A, and so the intersection is going to be this region. So I claim that this is it's analogous to what we have up here. So A intersect B union A intersect C. So notice that this region is A intersect B, which is that, union A intersect C, which is that. Next, we have A union B intersect C. So let's draw a picture for this. So this is A, this is B, this is C. So now A is, let's see, so I should say this is A, this is B, this is C. So A union B intersects C. So B intersects C is this region here. So now what we get is the circle A plus this little sector B. So I claim that this is actually, so it's analogous to the distributive law up here. It is A union B intersect A union C. So this might be a little harder to see, so just harder to draw. A union B is this region here, and A union C is this region here. That's not that bad. And so what is in both of these, I hope you convince yourself that the shaded region is precisely the common region to both of these things. So this is technically the left distributive law. There's also the right distributive law, which says that if A, let's say A union B intersect C, and A intersect B union C, that these distribute exactly how you would think. A union C, A intersect C union B intersect C. Again, it's the same thing as if these were addition and multiplication. And similarly, this is A intersect C union B intersect C. Okay, so that's the case when you have three sets. And of course, there's a similar, if you have A plus B times C, that's, of course, AC plus BC. Finally, I want to leave you with the general case, which is the distributive law of a set and a union not just of two sets, but of n sets. And similarly, a union with an intersection of n sets. So notice that what we just did was the special case when n equals 2. So I'm not going to do both of these. I'll do one of them. I'll tell you that the first one, what you actually get is the union from I equals 1 up to n of A intersect BI. So it's the union of n intersections. And I'm going to let you fill in the second one analogously. That said, we don't yet quite have the tools to prove this formally and rigorously. It's one of those, you can't do it for all n, but the pattern is obvious, so how do you formalize that? That's something that we will see how to do later in the class when we study proofs. Okay, so pause this video, see if you can finish this last identity, and I will see you next time.